Good morning, students. In last lecture, we introduced some basic properties of vector space. Now, in this lecture, we introduce new concept of subspaces of vector space. So, first of all, what is the definition of subspace? So, the definition says that let W be a non-empty subset of a vector space V. Here we have considered V as a vector space. W is non-empty subset of vector space V. Now, W is said to be a subspace of vector space V if W is a vector space under the same operation of vector addition and scalar multiplication as in V, which means that here we have V is a vector space with binary operation vector addition and scalar multiplication, and W is non-empty subset of V. Now, W is also vector space under the same operation as in V. Then we can say that W is subspace of vector space V. So, every subspace is also vector space. Okay? Now, these are some examples, trivial example. So trivial or improper subspaces. So, let V be a vector space, then it is known that V is subset of V. Okay, every set is subset of itself. So, V is subset of V and singleton 0. That means a 0 element or the 0 vector is also subset of V. Hence, V and singleton 0. That means vector space itself and singleton 0 both are vector space under the same composition of vector addition and scalar multiplication of V. That means now here V is the vector space and V is subset of V. So we can say that V is non-empty subset of V and V is a vector space under the same operation of vector addition and scalar multiplication as in V. So V is also subspace of V. And now here we consider singleton 0 or a 0 vector. It is also non-empty subset of V, and singleton 0 is also satisfy all the property to being a vector space. Okay? So, singleton 0 is also subspace of vector space V. Now, these two, V and singleton 0, are called the trivial or a improper subspace of V. Now, if we consider any other set than V and singleton 0, then this set are called proper subspace of vector space V. Okay? All other subspaces are called non-trivial or improper subspaces. Now, our next most IMP theorem is a non-empty subset W of a vector space V is subspace of V if and only if it is closed under vector addition and scalar multiplication defined in V. Or we can say that state and prove necessary and sufficient condition for a non-empty set W of vector space V to be a subspace of V. Now, these both are the statement of theorem. Now, what is the necessary and sufficient condition for W? We will see. The necessary and sufficient condition for a non-empty subset W of vector space V to be a subspace of V is that first condition is for all vector W1, W2 belongs to W gives the vector addition of vector W1 plus vector W2 belongs to set W, and for all alpha belongs to R and for all vector W belongs to W, alpha into W bar. This means scalar multiplication is also belongs to W. So first condition shows that set W is closed under vector addition, and second condition shows that set W is closed under scalar multiplication, because here it is the vector addition, here it is the scalar multiplication. So the necessary and sufficient condition for a non-empty subset W of vector space V to be a subspace of V is that W is closed under vector addition, that means first condition, and W is closed under scalar multiplication. This is the second condition. Now first we consider the if part, or say the necessary condition. So first of all we assume that W is a subspace of vector space V. Okay, first we have assumed W is subspace of vector space V. Now by definition W is a vector space under the same operation as those of V, because in our definition W is said to be subspace of V if and only if W is vector space under the same operation those of V. So here W is also vector space under the same operation as those of V. And now the definition of the vector space. First is closure property for the vector addition. Okay, from the definition of vector space we get first property. This is the closure property for vector addition, gives our first condition. Okay, that means for all vector W1 W2 belongs to W, the vector addition of this vector also belongs to W. So W1 plus W2 belongs to W. Okay, so this gives us our first condition. So now whenever W is subspace, we have first condition is proved. Now our W is vector space. So from the sixth property, that W is closure property for the scalar multiplication, gives for all alpha belongs to R and vector W bar belongs to W, alpha W bar belongs to W. These both conditions are obtained from the properties definition of the vector space, because W is our vector space. So necessary condition is proved. Now what is the sufficient condition? First of all we have assumed W is a subspace, then we have shown that the W is closed under vector addition and W is closed under scalar multiplication. So we proved first two conditions. Now we assume that these two conditions are satisfied. So this is the converse part, or we can say that a sufficient condition. For that let W be is a non-empty subset of V. Here we have considered W as a non-empty subset of V. In first part we have considered W as a subspace, but here we consider W as a non-empty subset, and then we prove that W is a subspace. Okay, so here W is a non-empty subset of V and satisfy these two conditions. Okay, first is the for two vector W1 bar W2 bar belongs to W, vector addition of these two vector belongs to W, and also for the scalar multiplication. Now our aim is to prove W is a vector space under this vector addition and scalar multiplication. So here now our aim is to prove that W is a subspace of V. Okay, for that we show that W is vector space under the operations vector addition and scalar multiplication of V. For that we proved 10 conditions for the vector space. So first is the closure property for the vector addition. This is already given in our hypothesis. What is hypothesis? We have considered W as a non-empty set and satisfy the two conditions. Okay, so closure property for the vector addition is already given. Okay, now the second is commutative property. For that let us consider two vector W1 W2 bar belongs to W. Now W is non-empty subset of vector space V. So these two vector are in W, but W is subset of V. So these two vector also in V. Okay. So W1 vector W1 vector W2 belongs to V. Now V is already given. V is a vector space, and vector space in these two elements are from vector space V. Hence they satisfied commutative property. So W1 bar plus W2 bar is equal to W2 bar plus W1 bar. So commutative property is satisfied. Similarly, associative property, here we have considered three vector W1, W2, W3 belongs to W. Now W is non-empty subset of V. So these three vector are also belongs to vector space V. Now V is the vector space and these three elements are from the vector space V. So they satisfied associative property. So W1 plus W2 plus W3 is equal to W1 plus W2 plus W3. So associative property is also satisfied. Now the existence of zero vector. Now our second condition is alpha dot vector W, that means scalar multiplication is also belongs to W for all alpha belongs to R. For that, here we have considered vector W bar belongs to W. So our fourth property is existence of zero vector. So consider vector W bar belongs to W. Now if we put alpha is equal to 0 in second condition, okay, our second condition is alpha dot W bar belongs to W. Now if we put alpha is equal to 0 in second condition, what we get? 0 dot W bar means vector scalar multiplication of any vector with 0 gives the 0 vector. So theta is also belongs to W. So existence of 0 vector is done. So where theta is a 0 vector. Okay. Now existence of additive inverse, okay, or we can say inverse element. For that, consider vector W bar belongs to W. Put alpha is equal to minus 1. In existence of 0 vector, we put alpha is equal to 0. But here we prove the existence of additive inverse. For that, put alpha is equal to minus 1 in our second condition. So that we get alpha dot W bar is equal to minus 1 into W bar is equal to minus of W bar belongs to W. So this minus of W bar, this additive inverse also belongs to W. So for every vector W bar belongs to W, we get the additive inverse minus of W bar also belongs to W. So fifth property is also satisfied. Now closure property for the scalar multiplication is already given in our hypothesis, because first of all we have considered W as a non-empty set, and then after that in second condition is closure property for the scalar multiplication. Now seventh property, for that consider two scalar alpha beta belongs to R and vector W bar belongs to W. Now W bar is a subset of vector space V. So this vector W bar is also belongs to vector space V. Now V is a vector space, hence it satisfies this property. That means alpha dot beta dot W bar is equal to alpha beta dot W bar. Okay. Now our eighth property is distributivity over vector addition. Now whenever distributivity over vector addition, we have considered two vector and one scalar. So let's consider one scalar alpha belongs to R and two vector W1 bar W2 bar belongs to W. Now as similarly as follow. W is subset of vector space V, so these two vector W1 bar W2 bar belongs to V, and V is a vector space. So by the definition of vector space, these two vector and alpha belongs to R satisfy the distributivity over vector addition. So here in case of W, we get alpha W1 bar plus W2 bar is equal to alpha W1 bar plus alpha W2 bar. Okay. Similarly, we can prove distributivity over scalar addition. For that, let us consider two element alpha beta belongs to R and one vector W bar belongs to W. Okay. By similar method, here W is subset of V, V is the vector space. Okay. So this vector W bar is also belongs to V. Okay. Because W is subset of V. So any element from set W is also element of set V. So W bar is from the set belongs to set V, and V is a vector space. So these two scalar alpha beta and vector W bar satisfy the distributivity over scalar addition. So this vector W bar from the set W is also satisfied the distributivity over scalar addition. So we get alpha plus beta W bar is equal to alpha W bar plus beta W bar. Now last property is unit vector. For that, let us consider similar method. W bar belongs to set W. Now W is subset of V. This implies that this vector belongs to V. Now V is the vector space. So this vector W satisfied this condition 1 dot W bar is equal to W bar for all W bar belongs to W. Hence W satisfies all the properties of vector space. Okay, W satisfies all the property of vector space. That means W is a vector space. Now W is vector space under the same operation as those of V. These are the vector addition and scalar multiplication. So W is a subspace of V. This gives the proof of our theorem. So what we have done in this proof? First of all, we have considered, let us so what is our aim? Our aim is to prove this statement or a theorem. So what is the statement? The necessary and sufficient condition for a non-empty subset W of vector space V to be a subspace of V is that first condition shows that W is closed under vector addition. That means for all W1, W2 belongs to W, the vector addition of these two vector W1 plus W2 belongs to W. And second condition is W is closed under scalar multiplication. That means for all alpha belongs to R and for all W bar belongs to W, we have alpha dot W bar belongs to W. Our aim is to prove this statement. Okay. So first we have considered necessary condition. So what is the necessary condition? For that we have considered W as a subspace. Okay, then we have shown that W is a subspace. So W is vector space. So from the definition of vector space, first condition is closure property for vector addition, and our sixth condition is closure property for scalar multiplication gives these two conditions. Okay. In this way we conclude our first part. Now for a converse part, for a sufficient condition, we have considered W as a non-empty subset. Okay, then and W is non-empty subset satisfying these two property. Okay, then we want to show that W is subspace of vector space V. To show W is subspace, we have to show that W is a vector space under the same binary operation. For that, we satisfied all the 10 properties of the vector space V. Okay. So in this way we proved all the theorem. Okay. So this is enough for this lecture. Now in the next lecture we also saw some important theorem, and we will see some examples of subspaces. Okay. So thank you.